Today we're very lucky to have Professor Alan Marscher from Boston University to talk about Blazar jets. And it's part of our series on XP and X-ray polarization, which finally provides us information on magnetic fields, which in Alan's case, you can use to compare to the radio polarization information, which has existed for decades, basically. So, we're going to see what we learn. And okay, yeah, I'll start introducing. So, Alan, I guess for those of you who don't know, probably most of you do know, is an expert in sort of VLBI, very long baseline interferometry and radio, making images at extremely high resolution. And he was a thesis student at NRAO back in the old days in the 70s, I think. And after that, he went to that says NRC postdoc at Goddard, and then UCSD, and then landed at Boston University, where he became chair and grew the department by quite a lot. And I ran to Alan. I don't know if he remembers, there was a conference in Socorro around 1987, and Roger Blanford was supposed to go, but he had to cancel last minute. And at that time, you could still board airplanes without ID checks. So he just handed me his plane ticket and said, "Go to Socorro." And Alan was there giving a review talk. And already at that time, he was an expert on all the things having to do with blobs and superluminal motion and the complicated things that we know have happened in radio for a long time, and now may be happening in X-rays also. And he's done lots of things. He's got his fingers in many pies. He's been doing some theoretical modeling of turbulent multi-zone emission, which has been a thing in the radio for a long time, and just starting to enter in gamma rays. He's been doing multi-wavelength observations with X-rays and gamma rays. He's on, for example, the users committee for the Fermi telescope for gamma ray telescope for a while, and he got the Rossi Prize as a member of the Event Horizon team, where I think he was the chair for the imaging group. And most recently, when the IXP project came together, they needed someone to lead the Blazar working group, and who else to pick but Alan. And so he's going to be here today to tell us about what's going on in X-rays. And my impression is that yes, the objects where we thought that the X-ray emission was synchrotron, these sort of high peak BLX, it is indeed polarized, and then life gets much more complicated after that. And maybe Alan will tell us about it. So without further ado, let Alan go forward and tell us about blazars and X-ray polarization and things like that. Okay,
Oh,
go for it, Alan.
yeah. Thanks for the very generous introduction, Paulo. Yes, so I want to try to put together a lot of the observational data and theoretical thoughts that have gone into trying to understand blazars at this really good moment in history of the study of blazars, where we have lots and lots of multi-wavelength data ranging from images to light curves to polarization versus time and other information. Okay, these are the main instruments that we've been using. My main collaborator is Dr. Svetlana Jorsad, also Boston University. She's also my wife. But we've involved many students and collaborators from around the world. Many of you are probably among the collaborators that we've been working with. We get funding from NASA and the National Science Foundation. I hope we continue getting funding from those places, but things are going to get tough these days. So I don't want to take very much time introducing blazars, since I think most or all of you know a lot about them. But basically, they're active galactic nuclei, where we think the jets are highly relativistic, and one of them is pointing right at us, and that causes things change in the jet. That causes variability, and the fact that they're pointing at us beams radiation to give a higher flux and also more rapid variability than you would otherwise get. You can see that when we do multi-wavelength studies, that it's relevant just by looking at this one mega event from 3C454.3 back in 2010, where there is an enormous gamma ray outburst. At the same time, there's an optical outburst. At the same time, an X-ray outburst. At the same time, there's an outburst even at millimeter wavelengths. And so it's the same population of electrons and the same magnetic fields and so on, that, at least in this case, are going into the highly variable non-thermal emission that we see. When we look at images, we find that most of the action tends to occur at the high energies. Most of the action seems to occur in what we call the core of the jet. The core of the jet isn't probably right at the black hole. It's downstream of the black hole. It's just a place where the jet is beamed well enough, and there's enough acceleration of electrons and amplification magnetic field to produce lots of radiation. And you see that during the same time when there was this multi-wavelength outburst, we saw the core of the jet increase in brightness tremendously. If we look at the spectral energy distribution, we can kind of split the blazars up into three categories: a low synchrotron peak, where if you look at the synchrotron portion of what we think at least is the synchrotron portion of the spectral energy distribution, the SED, it peaks somewhere in the infrared part of the spectrum. And then there's another peak up in the gamma ray part of the spectrum. So those are the low synchrotron peak, whereas the high synchrotron peak, like Markarian 421, a BLAC object, the peak is in the ultraviolet or X-ray part of the spectrum. And then the gamma ray peak can be way up in the above a GeV, up in the tens or hundreds of GeV region of the spectrum. There's also the intermediate synchrotron peak blazars, where the peak is somewhere in between, or actually can go back and forth from peaking somewhere in the infrared or optical part of the spectrum to peaking up in the ultraviolet part of the spectrum. So here's just a graphic that compares them. So for the HSP sources, high synchrotron peak, the synchrotron peak is usually in the ultraviolet or soft X-ray part of the spectrum. The LSP, the peak is in the infrared and up here in the gamma ray, and then the intermediate synchrotron peak is in between. The range that we can observe with the IXP telescope that's in orbit, and then can measure the X-ray polarization between 2 and 8 keV, that parts, you can see the synchrotron part of the spectrum in an HSP, whereas it's whatever is causing radiation here, probably Compton radiation here in the ISP or the LSP sources. Now, onto the variability, you can see that the variability is really rampant in objects like this. On the left is a quasar 3C 454.3 that had these huge outbursts I showed a little bit earlier. And it's kind of characterized by having enormous outbursts, you might call floods of multi-waveband flares. And then in between there are droughts of very little activity. And you see that when you look at the VLBI images. You can see also that the jet becomes fairly quiescent during these drought periods, and it becomes a lot more active, sending out lots of blobs during the high energy active periods. You see if you look at the optical polarization, you see the polarization is highly variable, and also the position angle of the polarization is highly variable. You can play a game with the position angle of the polarization and say, okay, since there's a 180-degree ambiguity in the polarization position angle, then you can say, okay, anytime there's a gap between observations, let's have it jump in the direction that gives you the smallest change in the position angle. And then you get something like this. You see that the scale here is much different from the scale up there. And you see that sometimes you get rotations of the polarization that can be by accident, can be just some kind of turbulent process going on, as I'll describe a little bit later, or can be caused by things that are kind of rotating around inside the jet. Oops. Here's an ISP source, 0716 plus 714. You can see similar sorts of variability. You don't get usually get very long droughts of inactivity, but also you'll see very strong changes in polarization. And then if I go to another ISP source, a BLAC, you can see kind of a change in behavior from a time when the optical polarization is always highly variable in terms of degree, but the position angle can hang around the jet direction, which here is about plus 20 degrees. You see the position angle here is about 20 degrees for a long time, during a time when the source was fairly quiescent. But then when it goes into outbursts, now the position angle becomes a lot more variable. And in fact, as we publish, we see some rotations of the polarization. If you look on short time scales, as was done in this so-called NOPE campaign that led by Yanis Liadakis a couple of years ago, you can see that on time scales of less than a day, you can get really high, strong variability. Here's another campaign from Gopal Bhatta that he led on 0716 about 10 years ago. And you see again the high variability in flux and in polarization degree and polarization angle. And the variation is over hours. So it's clear that there's some really kind of stochastic process going on that we'll call turbulence, whether it's exactly fully developed turbulence or not, let's call it turbulence. So how do we get these changes in polarization? I learned this from Tom Jones, who's in the audience out there, that you can take an old model by Byrne from 1966 and say, okay, let's just break up the source into a bunch of equal size cells, and that each cell has its own uniform magnetic field, but the direction of the magnetic field changes from one cell to the next in kind of a random way. If you do that, and then you keep cycling the cells to come in and out of the emission region, then, and if you have n number of cells, then the average polarization that you get is equal to the maximum polarization for synchrotron radiation, which is in the 70-75% range for most spectral indices, divided by the square root of the number of cells that you have. An important thing that Tom found and we kind of, our group got a little more precisely calculated, is that the polarization varies about that mean with a standard deviation, which is about equal to the mean divided by 2. So not only do you get lower polarization than the maximum value of 70-75%, but you also get variability of the polarization from this kind of simplistic picture. So if we just do that kind of picture, here's a simulation, and you can see that sometimes you can get, you see the scale here, this is from 0 to 500, and here you see a rotation by about 700 degrees. That's just a random apparent rotation of the position. It looks fairly smooth. It's not completely smooth, but it looks fairly smooth, which is sort of surprising. And you see here the variability of the polarization and the how that changes as really follows this law fairly well. Okay, now since we have not only just a randomly changing polarization, but we also have polarization that can hang around the jet direction for quite some time, we have to have some way of organizing the magnetic field so that despite this randomness that's inherent in the source, probably from turbulence, that we also can get some degree of ordering to give us this this preferred direction of polarization. So one way of doing it is through a shock wave. Here you see this line here represents the shock front. And here I've drawn magnetic field lines that if those magnetic field lines then pass through the shock, then you get some stretching out of the field lines. You get some amplification in a direction that's perpendicular to the shock normal, and no amplification in the direction of the shock normal. So you can see that here you have some partial ordering of the magnetic field, where here it was just randomly oriented. And that gives you some preferred direction of the polarization. That preferred direction of the polarization is along the shock normal, which, if the shock is a square wave moving down the jet, would be in the direction of the jet. So from a shock moving down the jet, you expect to get some fairly high degree of polarization, maybe tens of percent on average, and that the position angle will be along the jet direction. You can also order the magnetic field just by having an ordered magnetic field in the jet. And one of the favorites for the people doing magnetohydrodynamics of jets is a helical magnetic field, which is pictured here. It looks kind of like a spring seen side on. You can also have a toroidal magnetic field. And then here's the helical magnetic field, where the your offset. Here's a side view, and this is a view from another angle. Okay, so you can superpose these so that you can have a helical magnetic field, for example, along with shocks, along with turbulence, to give you the kinds of patterns that we see in blazars. So the shock can compress the magnetic field to make it more perpendicular to the shock normal. And here I have simulations where we have a helical magnetic field. 20% of the magnetic field is in the helical component, 80% is in a turbulent component, and the helical pitch angle of the helix is 45 degrees. And so you see some variability of the flux here caused by that. You have some random event here that looks like kind of a pronounced blazar flare. And here you see the degree of polarization varying kind of according to the prescription that we gave on the last slide. And one of the interesting things that I found in doing these simulations is that the direction of the mean direction of the polarization position angle doesn't have to be along the jet direction. If you have a helical magnetic field that you're looking at, it's some direction. So if the pitch angle of the helix is not close to 0 degrees and not close to 90 degrees, then you can have an average position angle that's offset from the jet direction. So looking at real sources, BLAC again. This is during an event that's chronicled by Gudo et al. In a paper that's just now being published in APJ Letters. In November 2023, we had an IXP campaign during that time, and the time of the IXP campaign is shown in the gray here, grade shading. And also we did optical polarization and radio polarization, millimeter wave polarization. And you see that the optical polarization got up to over 47%, which is as high as blazars get. So the magnetic field became nearly uniform in the optical emission region. However, in the X-rays, we got only an upper limit. It was integrated over this entire time, but it was only an upper limit of 7.4%. So that's consistent with the picture that in the radio to infrared, you get synchrotron radiation, but then in X-rays, you get Compton radiation. So when you have Compton radiation, the polarization is considerably lower than in synchrotron radiation. You can have the seed photons can be from, say, emission line photons or something like that, in which case you don't expect to see any polarization at all in the X-ray. Or it can be synchrotron self-Compton, where you have a reduced polarization, reduced relative to the synchrotron. Now, the position angle of the polarization in the optical changed by about 50 degrees during this time. When you have a changing position angle, you then dilute from vector averaging, because perpendicular polarizations cancel. By that kind of vector averaging, you decrease the polarization. But still, even given that, you should have gotten polarization of about 25% in the X-ray if it were exactly coincident with the optical emission region. So the fact that you don't, you can explain that with synchrotron self-Compton, or with external Compton, where you have seed photons from dust, dusty torus, for example, or seed photons from broadline region. In a previous result by Pearson et al., we measured a steeper X-ray spectrum and detected an X-ray polarization of 22 plus or minus 7% at 2 to keV, not at the harder band by XB, but in the softer XB band, we measured a polarization which is fairly high. And so that was a time where apparently the synchrotron radiation shifted, so where the highest energy, highest frequency synchrotron radiation was up in the X-ray part of the spectrum. And here I list the observations that we have of HSP sources with XB. So it's not too many that can't list it. On the other hand, it is too many to be able to digest this very easily. Essentially, if you look at the ratio of the X-ray polarization, the optical polarization, you get a ratio of between 2 and 7. So the X-ray polarization is almost always stronger than the optical polarization. The X-ray position angle is sometimes similar to the optical and sometimes not, and sometimes similar to the jet direction and sometimes not. So we still have, I think, a lot more observations to do before we can see exactly what the trends are. And no X-ray polarization has been detected yet for any object that's the full-time LSP source. That is always an LSP source. Herman Marshall led a paper on that. It's published last year. Here's the well-known VLAC object Markarian 421, which is very nice to observe because it's always bright in the X-ray, and it's also usually a source of very high gamma ray energies. You see that, sorry, that it behaves in a similar fashion to the other blazars in terms of the variability of the gamma ray. It behaves like a VLAC object with the variability of the gamma rays. Being somewhere around a factor of 10 in the GeV region, stronger variations in the TeV regions, and very strong variability in the X-ray, which is often well correlated with the gamma ray, sometimes not, and variability in the optical. In the optical, the galaxy provides fairly strong flux of starlight. So you have to subtract that if you want to just see the non-thermal stuff. So we think we know how to do that. And so this is with the starlight subtracted. Here in the polarization, also with the starlight, which is unpolarized, subtracting that so we don't get any dilution, you see that the polarization hangs out around 5% or so, but varies a lot. And the position angle varies a lot as well, although it tends to be not straight too more than a few tens of degrees most of the time from the jet position angle, which is in the pink range here. Markarian 501, kind of a sister object to Markarian 421 in a lot of ways. However, its variability looks very similar, but in the polarization position angle, you see it really hangs out around the jet direction, which is again in pink here. A little bit offset, but as I showed that if we have turbulence and shocks and helical magnetic fields, then you can have the direction of the polarization to be a little different from the direction of the jet, or possibly the jet can bend so that the jet has a somewhat different direction upstream in the X-ray part of the jet, X-ray emitting part of the jet, than it does downstream in the part that we can measure in the optical. Okay, so again, this sort of behavior where you often have organized polarization and often don't, I think can be explained well with turbulence and shock, and in this case, in order to explain the offset of the direction of the polarization from the jet direction, to have a ordered helical magnetic field that's offset with a pitch angle of the helix, which is something like maybe 70 degrees or so, instead of 90 degrees. Okay, so we have the observation that the polarization, the degree of polarization in the X-ray is about 2 to 7 times greater than the optical in our observations. So how can we explain that? Well, we can go back to to a model that I proposed back with Walter Gear back in 1985, where you accelerate electrons at a shock front, and then as the electrons propagate away from the shock front, they lose energy, and the highest energy electrons lose energy faster than the lower energy electrons, and the high energy electrons become lower energy electrons as they lose energy, so that the only place where you can get strong X-ray synchrotron emission is very close to the shock front. As you get farther from the shock front, in green here, then you only have lower energy electrons. They can emit in the optical, but not in the X-ray. And so in the region here in the X-ray, you have a small volume, and a small volume will sample a relatively small number of turbulent cells. And so that will tend to give you a higher average polarization plus a higher variability in the polarization. And then if you go to a larger volume that you can emit in the optical, now the X-ray part can also emit in the optical here. So this whole thing emits in the optical, it will have a lower polarization because you're sampling over a larger number of cells and a lower range of variability as well. You may also have extra turbulence as the plasma propagates away from the shock. It may become even more turbulent. The turbulence becomes stronger, then you also will get some more dilution of the polarization. So the polarization will get lower in the optical. One advantage of this kind of model, this what we call energy stratified model, is that if you take a look at the SED of Markarian 421, it really looks like if we could observe in this forbidden ultraviolet region where the dust in our galaxy blocks the light, you can see that it looks like it should connect smoothly. So either you could have a complicated model where this then curves down and this curves down here, coincidentally at around the same frequency, or this is all just one continuous region where here this is a smaller volume, but it's still part of the larger volume that emits in the optical. And so that can, and here in the gamma ray, you then expect to have a similar smoothness of the SED as you go from ahead of the peak to behind the peak, lower energies than the peak. You don't expect to get that from a you have say X-ray are coming only from a spine, and the optical is coming from some sheath surrounding the spine, but the two aren't really associated otherwise, not strongly at least associated otherwise. You don't expect to get this kind of smooth connection of the SED as you go from higher to lower frequencies. Okay, so here's my cartoon that I'd like to show that of kind of the basic model for a Blazar. It's just an active galactic nucleus. When you're not looking right at the jet, you got an accretion disk that's temperature stratified, and so you have a black body emission that's peaking at different wavelengths corresponding to the different colors here. You have a corona that of hot electrons that scatter the accretion disk photons up to X-rays. You have a jet that comes out that has a strong helical field confining it at first, and then it gets into equipartition between the kinetic flux and the helical magnetic field, and then it can become unstable and generate turbulence through kink instabilities and other kinds of instabilities. Then if you have a pressure mismatch with the external medium that you expect to have, let's even if this, well, this, for example, could be the Bondi radius here, and then you get a conical shock in the shape of a cone, then you get a rarefaction behind the shock, and so you can get particle acceleration can occur in the turbulent region from a lot of relatively small magnetic reconnections, and also some second order Fermi acceleration. And then when the plasma crosses the shock, it gets accelerated some more by diffuse shock acceleration. And some of the cells, turbulent cells, will have magnetic field direction that's favorable toward having the electrons jump back and forth across the shock and to gain high energies. And so some of the cells will have high enough energies to produce X-ray synchrotron radiation, for example, or very high energy gamma rays. You can also have and seem to have shocks that are moving down the jet that are can appear as superluminal blobs in the radio images, in the VLBI images. So lots of stuff going on. So I made a numerical model that incorporates all of this, where I have many turbulent cells, thousands of turbulent cells. And you look at sideways, you can see all these cells. I assume that the emission that I'm going to be modeling starts right at the shock front where the electrons are reaccelerated to higher energies. And so this is where you get all the action, and then they lose energy as they move away from the shock front. If you're looking face on, then it looks kind of like a Gatling gun. If you look at side on, then it looks something like this. So each cell, as the simple model from Bern, each cell has a turbulent and ordered magnetic field component. Actually, no. Each cell has a magnetic field, the magnetic field and its own magnetic field direction. And the component of the magnetic field can come from turbulence, it can come from an ordered component. And then the shock the shock jump conditions will cause some compression of the magnetic field, as I showed before, along the shock normal. And so the flux of the polarization will fluctuate as you see the changes in the magnetic field direction, the changes in the electron density and energies of the electrons as they cross the shock and move downstream. You can have major perturbations. The whole flow can change. So you can put in a changing input of the energy density coming down the jet. And an important feature, as I was just describing, is only a small fraction of the cells get electrons high enough, electron energies high enough that they can accelerate, they can produce X-ray synchrotron emission and gamma ray Compton emission. And because you only have a small number of cells that can do this, the emission will vary more rapidly. And then you can explain the intraday flux changes. Also, the SED above the peak frequency will curve downward because you're getting smaller and smaller number of cells that can radiate at those higher frequencies. So it looks fairly similar to log parabola that is often used to model the SEDs of Blazars. If you assume that instead of a power law distribution of electron energies, instead if you have a log parabolic distribution, then you get a downward curve of the spectrum below the curving away from the power law, whereas you can get the same thing from this kind of model. One thing that this model can do was found by Tim Cawthorn, and then I used my TEMS model in order to verify that, is that you get if you're looking almost right down the jet, then you get a polarization pattern where the position angle is kind of radial. Plus you get an offset of the degree of polarization peak. You get an offset upstream of the polarized intensity relative to the total intensity. Here the total intensity is in black and the polarized intensity is red. And so the polarized intensity is upstream. And that's what we see in Markarian 501, for example, where you see the polarized intensity is upstream of the total intensity, and you see the radial polarization pattern. So we can reproduce that sort of thing that's otherwise fairly hard to explain. Can also reproduce the intraday variability. Here's the data again that was gathered by Yannis Liadakis' collaboration during the campaign. And you see it goes polarization, the flux goes up and down, the degree of polarization goes up and down, the position angle wobbles around or swings around, and we get the same thing out of the TEM simulation. Get this essentially the same number of and this is for a magnetic field, it's 90% turbulent, 10% helical, but the helical is being seen side on. So you get about the same number of reversals of the direction of the polarization, about the same number of peaks in the degree of polarization in the model. It doesn't, though, reproduce. These are fairly expensive simulations, and the simulation we made don't reproduce very well the distribution of the polarization degree angles values. That is, the polarization degree was somewhat higher on average in the simulation than it is in the data. I don't consider that to be a very serious issue. It just have to run more simulations. And of course, because of that, because you have so much stochastic, in order to produce the turbulence, they use the old scheme by Tom Jones, where you choose randomly the direction of the magnetic field, and also randomly around some distribution the magnitude of the magnetic field, and then you have each cell is nested in a larger group of cells, larger zone of cells, so you can nest up to several zones, and then you apply the Kolmogorov spectrum, where the magnetic field direction from the larger zones counts more than the magnetic field direction in the smaller zones in order to produce your simulated turbulence. Okay, so another observation that we want to reproduce is the X-ray polarization fluctuations of Markarian 421, which is bright enough to be able to follow the X-ray polarization changes on a fairly short time scale, a time scale of about half a day or so. Here we have, and I hope that all of you can see these fairly faint cyan points. The cyan points are X-ray, and they kind of jump around in percent from somewhere around 6% or so up to about 25%. And the optical, it changes less, although it does change, hanging around 4 plus or minus 2% or so. And the optical tends to hang out more or less along the jet direction, whereas the X-ray, it changes by quite a bit. The fact that there's some change in the X-ray polarization position angle means that as you integrate, you're going to have some decoherence of the polarization degree. So the polarization degree is actually, in some of these cases where the position angle is changing fairly rapidly, the polarization degree is probably somewhat higher than what we can measure with XP because of the amount of time we need to integrate in order to get a detection. Okay, so we measure an average of 13% for the X-ray polarization, measure an average of 5% for the optical polarization. As I said, the X-ray is probably somewhat higher. So it's probably a ratio of 3 to 4 times the optical degree of polarization. The X-ray degree of polarization is 3 to 4 times higher. Okay, so I want to see if what I can reproduce with the with my TEMS model. Excuse me. And what I end up using to reproduce the variability is a model where the magnetic field is 70% turbulent, 30% helical, and the position angle or the opening angle of the helix be 80 degrees, pitch angle of the helix to be 80 degrees. And so you see the flux variations here. You get interesting, as you might expect, you get time delays where the X-ray synchrotron peaks first, and then you get the optical to peak a little bit later. Interestingly, the TeV, because in order to make the TeV from Compton scattering, you need to wait a little while for the seed photons from synchrotron to get to the places where they're going to be scattered. There's a slight delay between the X-ray and the TeV peak, and then you have the optical peak being a couple days later. As you expect, you get, as similar to the observations, you get a much lower optical polarization than you get X-ray polarization most of the time. And the position angle, while they kind of seem to follow each other over fairly long periods of time, over short periods of time, they don't so well. And so a typical observation that we'll get with IXP, even for the longest integrations we have, will be about 15 days. So I took a few random times 15 days, 15-day intervals here, and plotted on the right side what it will look like. And so even though you can see that the X-ray, optical, and TeV follow each other quite well on the long-term light curves. On the short-term light curves, it doesn't really look like they do all that well at all. You wouldn't get a very good correlation if you do a correlation study of this. And the degree of polarization, you see the optical really kind of floats around very gently. And so it doesn't look like, even for the position angle, it doesn't look like the two have very much connection, whereas you can see on the long-term curves that they actually do have a strong connection. Here you can see connections maybe a little bit better, but you have to be guessing. Is this really related to that? Is really related to that? You can see on the long-term curves that yes, they are related, but for a 15-day campaign, it's not so easy. So you really need to do a long-term monitoring. Here's another time range. Finally, I wanted to emphasize that these models that we're making, even though they have all this complexity in them and they're starting to explain some of the complexity in the data, nature can be a lot more complex than what we're allowed to do, simply because we don't want to have too many free parameters. Here is the Event Horizon Telescope image up here, and the image at 1.3 centimeters. It's a factor 10 higher, a longer wavelength, factor 10 lower frequency than the Event Horizon Telescope one, which is 1.3 millimeters. And you can see that when you look at it with, this is using the radiostron antenna, which is up in space, so you get a much longer baseline than you get from Earth-based arrays. And from that, you can see a filamentary structure to the jet. Now, the cartoon that I drew didn't have any filamentary structure, didn't have any structure in the transverse direction. It was all the structure was in the longitudinal direction. This is a VLBA image from our VLBA survey or VLBA monitoring, where it's a lower resolution. This all fits into here, between there and there. And then the Event Horizon Telescope is looking at this region in here. So here we see that, you see some contours from the radiostron image, radiostron plus ground array image here. So this filamentary stuff means that you're not lighting up the whole jet equally, the whole cross section of the jet equally. And so there may be some kind of instability like Kelvin-Helmholtz instability or kink instability that's creating this kind of structure. But it's something that really in the future simulation should include. Okay, so to conclude, a working jet model that incorporates turbulence shocks and helical magnetic fields can explain a lot of the general properties that we're observing in blazars. The energy stratification explains the multi-wavelength similarities and the differences. So similarities, the continuity of the SED, and a lot of times the variability occurs in a similar way at the different wave bands. But there are a lot of differences as well, and the randomness that we have in the turbulence can help to explain those differences. In the case of these models, the ratio of the order to the turbulent field determines the level of variability, and that seems to vary from one source to another. Electrons are accelerated at particular locations and then lose energy as they propagate and radiate. That's really how we can explain the differences between the X-ray and the optical polarization, despite the fact that the SEDs connect smoothly. I want to emphasize that shock may not be the only way to do that. This maybe could be done with magnetic reconnection. If you accelerate electrons at a particular location, say through magnetic reconnection, and then they stream away from there and lose energy as they stream away, you might be able to get a similar connection between the X-ray and the optical polarization. The data include features that strain the model, as it's always the case. If you have enough data, then you're not going to be able to reproduce it very well with a model. So there's room for phenomena that I haven't put into the model that I'm working with, such as changes in the jet direction, magnetic reconnections, filamentation, like you saw in the image of 3C279, kink instabilities, and other instabilities. So even though there's a lot of complexities to the data are providing more and more constraints on models. But as I showed you with Markarian 421 example, we need to keep sampling the variability to find more patterns and also to find which patterns are reproduced. So we want to repeat observation of the same object as well as new ones, and to observe them as long as we can, to get as long a data train as we can. And so future instruments need improved sensitivity and throughput. There are a variety that are being proposed to get higher sensitivity, for example, in X-ray polarization, all sky imagers and so on, so you can get higher throughput, look at more objects in a given night. And also we need a lot more theoretical work to develop models that can be compared with the rich data sets that we have. Thanks very much.
Great. Thanks a lot, Alan. Okay, and now it's time for questions, and for the beginning at least, ask questions about the talk, and then we can expand it further from there. So, all right, we got two hands up. I think Henrik went first. So, Henrik, what's your question? Yeah.
I have a question. How clear is the case against reconnection, or how clear does this really how does really argue for shock acceleration, not reconnection?
Yeah, as I said in my last slide here, that I think you can explain it that way as well. I haven't done it, and I haven't seen anyone who's done a reconnection model that does it. Although in the last year or so, I haven't kept up with the literature as much as I'd like to. Yeah, what you need is to accelerate particles at a particular place, and then for them to stream away from that place. A shock model that was, it was proposed back in 1985, a shock model that does that sort of thing. So this had a lot more history, but magnetic reconnection, I'd like to see, somebody do some simulations to see what that's capable of doing.
Yeah, that makes sense. So Lorenzo Zironi, when we talk to him, he always says it could be done by reconnection, but it's right. It would be really nice to see actual modeling describing the data.
Yeah.
Yeah, I guess Hao-Cheng Zhang has done some of that, or he's got multiple cells. It's like what Alan said, I think, that do things separately. And then as long as things diffuse out and sample different spatial regions where the field order breaks down, then I think you get similar things. Maybe while I'm interjecting, a problem for Hao-Cheng and also other people is to get these rotations that seem pretty coherent. In like 421, I guess it took a whole day or 2 days for the X-ray polarization angle to change. It went smoothly, like
it can change in half a day.
Half a day, wow. By 180 degrees, or how much?
Oh no, not by 180. Sorry. Yeah, it's a couple days for 180 degrees. Yeah.
Okay, wow. Okay, Evgeny's got a question next, I guess.
Thank you for the talk. In one of your first slides, you have spectra for different kinds of lasers, low synchron peak, high synchron peak, and intermediate, which are not this one. Yeah, next, probably. Yes, as I understand, these are just drawn by hands, but I wonder if I can trust the feature that I see in the black line, the low synchron peak lasers, that the synchrotron emission apparently drops by more than 2 orders of magnitude at 10 to 15.
Let's see. Where is it? It's
from 10 to 15, the black line, from 10 to
here.
15
Yeah.
hertz. No, 10 to 15.
The high energy.
Yeah, the high energy part, yes. It's drops by more than 2 orders of magnitude. Is it just you have drawn it like that, or is it real?
Drops by 2 orders of magnitude. I mean,
In the high energy part, from 10 to 15 to 10 to 16, more or less.
10 to 15, 10 to 16. Yeah.
Yes.
I don't see the 2 orders of magnitude. This is 1 order of magnitude here, so it looks like it drops by about 1 order of magnitude or so. But yeah, it's from the power law being steepened by the smaller number of cells. So this is from they're just sketches, but they're from my TEMS model, where you have a smaller number of cells that can accelerate electrons to the higher energies. And so that's the bending down that I was talking about, similar to a log parabola.
But this is a model. This is not a real observation.
Yeah, it's a model. Yeah.
And the second question is about the variable blazars. You said, as I understand, that some of the blazars apparently change their appearance from low synchrone peak to intermediate or to high synchrone peak. Is this correct, my understanding? And if yes, do you think that they follow the general trend that as the luminosity increases, you move from the from the high synchrone peak to the low synchrone peak? Is that correct or not?
Yeah, I understand what you're saying. It looks like from that X-ray polarization observation of BLAC that you could detect the X-ray polarization at 22% or so during yeah, I'm trying to remember everything more exactly. So in terms of what the flux level was. So what the most important thing is that the highest energy of the electrons, gets to be high enough so that you can radiate in the X-ray part of the spectrum. In BLAC, we have kind of seen signs before by the changing of the X-ray spectral index. It becomes steeper during some high states where you have a synchrotron outburst, and then the spectrum becomes steeper. And so that's similar to what we see in the X-ray when you get the high energy cutoff to the synchrotron radiation goes to higher energies. Then we see a detect a polarization in the soft X-ray bands. I think you're right that does not go along with what is said for the so-called Blazar sequence. That is that the blazars that have the highest energy SED peaks, that those are lower luminosity objects. So yeah, I think your perception is right that in this case it doesn't follow that, so that this population study that says that lower luminosities correspond to higher synchrotron peaks doesn't then extend to time variability. Sorry for taking so long to answer the question, but yeah, I think in BLAC, the SED peak moves around in a way that we haven't sampled well yet, but doesn't exactly follow this Blazar sequence.
And are there any observations of a peak position? What you are saying is a kind of indirect evidence, right?
Yeah.
But, are there direct observations of the peaks? No,
not in the ISP sources. We need to have far ultraviolet observations to do that.
Thank you.
Yeah, my own personal opinion is that the Blazar sequence doesn't work for individual objects. Like their tails can move around, and like 3C454 is a GeV Blazar, except in the 2000s it was an MEV Blazar sort of. So they kind of shift around. But maybe the correlation works if you average and look at a sort of large scale, there's a lot of scatter. That's my personal opinion, which is controversial. Okay, Marco, you're up next for a question. Yeah.
Yes, well, very nice talk, Alan. Always a pleasure to hear you. I have a couple of points. One is your simulation is able to reproduce the ratio of X-ray to optical polarization of factor of order 3 or 4.
Yes.
So you reproduce it with about 20% of the helical field and 80% of the turbulent.
For that particular simulation, yeah.
But is it general?
I should say that not all the simulations produce that higher ratio of,
okay.
And that I think that I had one slide where I showed that the turbulence gets stronger as the plasma moves away from the shock. I think that has to occur in some of the objects.
Okay, so the ratio can be different from 3 or 4 or 5, whatever. Can be lower in some way.
Yeah, if the turbulence doesn't become stronger as you move away from the shock, then it'll often be lower than factor 2.
Okay, and also we are not really helped by the relation, if any, that there should be between flux intensity in the optical and the X-rays and the polarization. So you show the example, I think, of Markarian for whatever.
4-to-1?
4-to-1, I think, where you chopped the light curve in different 2-week periods. And it was a very interesting analysis that you showed.
Yeah, okay. That was near the end, yeah.
Right, and right, that one, right. So the polarization doesn't really obviously relate with the flux intensity, right?
That's right.
But should we expect some sort of relation between the two?
It depends on what's causing the variations. Here, I've made the variations by varying only the N0 of the electron energy of the injected electrons.
Okay.
So if I vary the magnetic field as well, let's say I kept a partition of the input of the magnetic field and the electron population as it crosses the shock. If I made an equipartition, then you would have more of a correlation with the polarization, I think. For those simulations to really be able to a definite statement, but I can make the definite statement that sometimes there is a relation between the polarization and the flux, and sometimes not. I did show one example where see if I can find it, where there was an outburst.
Yeah.
There it is. Here on the right here.
So this is the simulation, right?
Yeah, this was simulation, yeah.
Okay, anyway, yeah. All right, thank you. Yeah.
All right, thanks. And maybe I'll interject one related question. One argument about the turbulent model, which I'm not sure happened, is like you have a maximum flux per cell, so and you have some variability in each cell, but then if you have n cells, you kind of divide the maximum amplitude you get by square root of n, so you never get huge variations because you have many sources on at the same time. And sometimes in these objects, you can have factor 2 variations in hours, or like one zone sticks out over everybody else. But and maybe that happened in this model here. But how do you is that a problem with observations? And too many zones don't produce so-called nonlinear variability, where you got a huge factor. It looks like one zone turned on.
Yeah. Okay. Good question. So I don't get variations only from turbulence. I also put in variations. I impose at least for a lot of the simulations, I impose a power spectral density on the density and magnetic field, electron density and magnetic field that are approaching the shock.
Okay.
So the upstream, so I changed condition upstream. So I changed the input parameters according to a PSD in order to
Okay.
produce a really, really large variability. However, I don't think that I did. I'd have to look, Paulo. I'm not sure. I don't remember what I did for this particular simulation, whether I did that. It looks like I must have.
Okay. Yeah. Because if you do that, I guess it all behaves as like one zone sort of.
Yeah, well, either that or else I had a small number of cells.
Okay. Yep. And do you think one zone ever dominates everything? Like in the radio, sometimes you see one blob outshine everything else. Does that happen? Or
Yeah, I think the TV observations tend to show that it does, right? That a lot of times you can model the SED during a TV flare. You can often model it as a single zone,
Mhm.
and the fact that you can model something so well with a single zone implies that sometimes that happens. And of course, with the BLAC, this event here where the polarization got up to 47% in the optical, that's getting close to just a single cell dominating, or or a cell being really big, a whole bunch of cells cooperating, so that one zone that's really big, really really high density magnetic field.
Okay. Yep. So the correlations. Okay. Thanks. Then Annalisa also had her hand up. So go ahead,
Hello, Alan. Nice
Hi,
talk.
Annalisa.
Thank you.
Thank you.
I have three questions. The third one has been already just asked by Paolo, whether you think that there is a dominant region, a region dominating the emission. But the other two questions are very naive. Can you go to the last slide, the conclusion slide of yours? Yes, here you, of course, in point 3, you say the more the better, the longer the better, of course,
Yes.
to constrain the model. But going back to point 2, in a more questionable way, do you think that there are observations which might not be consistent with your model, which can rule out? I don't want to be negative.
Yeah. Yes. What you're asking, is this a scientific model or is it just speculation? That's all. Often the difficulty when you're trying to explain something that is very that's very complex, and you try to explain it with a model that's very complex. Now you run into this philosophical problem of are you really doing things the proper way?
You don't see any obvious observation which can pose serious problems to the model.
Yeah, I would say that the multi-wavelength polarization, the model will predict a very specific multi-wavelength polarization. What I mean by that is what I would like to see is multiple X-ray energy polarization. So to have not just 2 to 8 keV, but have a wider energy range.
Okay.
And also in the optical, we've done some multicolor optical polarization observations, but I'd like to see more of that. And so the prediction would be that you have, as you go from harder X-ray to softer X-ray to violet to red and infrared, that you would have the polarization, average polarization would get weaker.
A systematic trend.
That's right, systematic trend. That's the main prediction, I would say.
Okay. And the last question, which is quite far off for what you said, it's about in your model, do you account or consider the extremely fast variability seen in TV, the 5 minutes variations?
I haven't tried to model that yet, but I think that this kind of model is capable of doing that. Because if I take a look at 3C279, one of the mistakes I think a lot of modelers have made is to think that the jet is a lot wider than it is.
Okay.
The jet, when we deproject using our VLBA data, when we deproject the jet, we find that the opening angle for most of these really powerful blazars is much less than 1 degree.
Yeah.
So we have an opening angle that's less than 1 degree, and here you can see why, and that's after watching it change direction from 1 year to the next.
Yeah.
Now if the jet direction that we see as it wobbles around, if that jet direction is that jet opening angle is less than 1 degree, and now you look at this filamentary structure and you see that this is less than the full cross section.
Yep.
Now you see that downstream in the jet, you can actually have very compact regions that that can vary quite fast.
Okay. Okay. Thank you so much.
Yeah, thanks. Okay, we're well past the hour, and we're gonna hang out till 10:30ish. And people are free to leave, are already leaving. And we can open up the floor to broader questions. So, anybody have other questions you've been burning to ask Alan?
So Alan, this is Tom again. I have to go. I just wanted to say very nice talk, very nice work.
Yeah, well, thanks for laying the groundwork for that, Tom. You're, as always, through my career, your stuff has always been very inspiring and helpful.
Yeah, I would echo that. Maybe related to the, I'll fill the blank space for now. Related to the last question you got, when my impression was as you got to higher frequency VLBI, the Lorentz factors went up, and if the jet opening angle is 1 over gamma, then the jets are narrower and narrower, and then how likely is it to statistically match the population studies you see? Like the Grand Unified Model of MEG has Lorentz factor 10 for LBLs, but you're seeing 30. And then if you look at variability in gamma rays, you can get 50 or more sometimes. Is there a problem with that? Are you just seeing like an individual little bullet aimed at you and there's some wider opening angle, like 5 degrees? So you just said
Well,
this is 1 degree.
I appeal to Matt Lisser's work. Matt has done some modeling. First, he did it with some smaller samples back when he was a graduate student with us, but now he's done it with a Mojave sample with hundreds of objects. And if you apply a model where there's a distribution of Lorentz factors in the population, then and there's a lot more with the low Lorentz factors and not as many of the high Lorentz factors, the statistics work out okay. But I wouldn't say that the higher frequency, for example, the 43 gigahertz speeds aren't systematically higher by much, I would say, than 15 gigahertz. There's some effect there, but
okay. My impression was in the ancient days in the 80s, whatever, you were getting Lorentz factors 10, and then as you got high frequency, it jumped up to 20 or 30. Is that just for a few objects?
Yeah, that's just for a few objects. Yeah, we don't have too many that are that high.
Okay.
3C279, this guy is one of them, though. We had in year 2017, when the image on the upper left there was made, that year the apparent speed was 37C. So the Lorentz factor is around 40.
Wow.
But 3C279 and 3C454.3 and 1510-089, there are a handful of those that are really extreme objects. And we don't see many other examples, or maybe no other examples that are like that are that fast.
Wow. Okay. That's good to know. And maybe in 3C79, are you have a blob coming out EHT, or I guess there are not multiple epochs, but do you see a lot of variations in ejection angle, so-called ejection angle, or?
Yeah, we're trying to figure out what's going on that object. There's motion, but we don't have a long enough time baseline to say exactly what the motions are in that upper left image.
Yeah.
So what I would like to think, given my model, is that the up in the upper left there in the northeast, that is the core, and that its width there is obviously resolved in the transverse direction, and so that corresponds to the width of the jet at that point. And then the other things are blobs. They could be, places where there's magnetic reconnection going on. They could be shocks that don't cover the entire cross section of the jet, or just blobs of plasma, or there could be another standing shock in the jet. So we need to, as usual, more observations are needed.
Yeah. Awesome. Any other questions? I can ask more questions, but Felix, he's another organizer. Any thoughts? If you're there. No. I guess he's not there. Okay, Jonathan, fire away.
Yeah, can you see me, hear me?
Can hear you.
Yep.
Fantastic. So there is a question by Elena in the chat. I can ask it after, or Elena can ask it. But my question is to broaden a bit the scope. Do you think your TMZ model could be extended to other jetted sources, say prompt phase of GRBs, say microquasars? Is it specific to blazars, or can we apply it beyond that?
Yeah, it only requires to have a jet with a standing shock. I hope to generalize it in the near future to have also to do for square wave shocks that are moving down the jet, but I haven't done that yet. There's a version that's available on our website of the code, so somebody else could take the code and use it. But I'm going to put a newer version up sometime in the next couple of weeks that has more sources of seed photons, for example.
Okay, great.
But it's mainly done for blazars, but it could be adapted, I think.
Okay. And the question by Elena, I will ask it if you don't mind, because she doesn't have a mic,
Please.
is regarding Mach 421 and the CTAO simulations that, or the simulations of light curves rather, that you have provided in the past to the AGN FLARE task force. Elena seemed to remember that your model was not able to produce 5-minute timescale variability, but she wonders if her memory fails her, or maybe if the newer model helped to reach such short timescales.
Yeah, I haven't tried to simulate that yet. I don't think that I ever. I think maybe somebody else said that my model couldn't do 5-minute variations, but I'm not sure.
Okay, so it's rather haven't rather than cannot.
I think I know where that comes from. It comes from the size of the cells. One of the problems with the model is that the cells are all assumed to have the same size. That's not really, the way nature is likely to operate. And so the size of the cell dictates the minimum timescale of variability that can be modeled by a particular simulation. So maybe it's right. Maybe 5 minutes. I'd have to look, but there is some lower limit to the timescale that I can simulate.
Okay. While I have the mic, can I ask you what determines the size of the cells? So, okay, besides the numerics, but is it the current length of the magnetic field? Is it the typical? What drives it?
I get it to match the observations. So the number of cells, as I've discussed, the number of cells determines the average polarization and the standard deviation of the polarization variations. So I take the size of the source, the size of the jet that I think applies, kind of judging by estimating from VLBI and from other considerations, and just take that size of the jet and then divide it by the number of cells that are needed to reproduce the polarization, the degree of polarization.
And have you tried to play the game to place, say, the emission region a parsec away from the black hole? So if I have that in mind, it's because I'm thinking about FSRQs that we see at TV images, and for them, we suspect that the emission region is sufficiently far away from the BLR to avoid the absorption.
Yeah, that's a free parameter, how far away it is from the
Yeah, but if you were to place it at 1 parsec, say, and knowing the opening angle that you discussed, then what would the typical size of a cell be, and does it match a physical scale that we know in this plasma?
Okay, so let's say that the polarization, average polarization is 10%. Then that will typically correspond to, because I've got some order in the magnetic field from the shock, that would probably correspond to somewhere around 5, let's see, I'm thinking my parameters now, about 60 cells in a cross section. Okay, so 60 cells in a cross section, and now I can then do, that means 10 cells across.
So I got.
I would take the size. I would take the size and divide by 10.
I get 2 milliparsecs, assuming a 1 degree opening angle.
Yeah, sounds about right. Yeah.
Okay, so that's still big. Thank you.
Yeah, but now you've got some rapid variability from the Doppler factor as well. But
thanks a lot.
maybe you've already corrected for that, maybe.
Yep. Yeah, these extreme objects cause problems, I think. But I've got a question from Jishuang.
Yeah, hello. I have a follow-up question that in these turbulent cells, if I understand correctly, there are also substructures in these turbulent cells, because when we're talking about turbulence, usually could talk about this cascade effect. Or it's a full spectrum for the magnetic field. So I was wondering if this would affect your model or not.
Yeah, I didn't get it. Have enough time to really explain whatever. I follow a prescription by Tom Jones to do a kind of rough simulation turbulence, where choose every cell belongs to several zones. Its own, a zone with 2 by 2 by 2 or 8 cells. Another one's 4 by 4 by 4. Another one that's 8 by 8 by 8. That's as far as the code has the power to do. And I assign, for every time step, I assign a direction of the magnetic field and amplitude of the magnetic field for each zone. And so a given cell is affected not only by its local change in the magnetic field direction, but also the change in the magnetic field directions of these different zones that it belongs to. So that gives you the kind of spaghetti pattern of the magnetic field that you get from real turbulence. But of course, what you really like to do would be to do a simulation with simulating the turbulence of physically simulating the turbulence in a size that's big enough in order to do this kind of calculation. But that's not computationally available at this stage.
I also have another question related to the flares within the multi-wavelengths. Some of these sources showing that flares in different bands, they have a sort of time delay. Is this also consistent with your model or not?
I'm sorry, what word did you use? Different bands, they do what?
They have a time delay in the flares.
Oh, time delay, yeah. Yeah, so here you can see, maybe I'll make it bigger here. Here you can see the time delay between X-ray and red is optical. It's a couple days, and between X-ray and the VHE is maybe half a day or so for that flare, for example. So yes, you see time delays because of the emission occurring in somewhat different regions.
Okay, thank you.
I think the observational data is not quite there yet, but people are trying to test that. Okay, we're running close to a half hour. Luigi, I got a question.
Hi, Alan. Sorry, just a quick question or curiosity, if possible. You didn't mention more specifically, but in the paper, in the last paper with BLAC, with the polarization of each spec on BLAC, with the flare and so on, you exclude a possible hadronic origin of the X-ray part. And I failed actually to see what is the reason that an upper limit of 7% basically exclude the possibility that, for example, it is a proton synchrotron. Given that if one looks at the electron peak, somewhat you can have exactly like in HSPs, optical polarization of a few percent, even, and I mean from low energy electrons, and you have high energy electrons that gives a polarization of 20 or 30%. But in all cases, we believe it is synchrotron. So I don't actually get the argument that you exclude a possible proton synchrotron origin.
Yeah, I won't take personal responsibility for that. I am a co-author on the paper, but that was done by others. That interpretation was done by others. But yeah, I think that it was just looking at some particular proposed models and trying to sort out which ones. I think it comes from a paper by Leodakis and a couple of others, a couple other people, Roger Vermani probably, and Pearson, who said that when they analyze the proton models, that they get the result. But also, I think it also must have come from Zhang, because Zhang was the main person who did the theoretical interpretation for that paper, for the BLAC paper, from Haocheng Zhang.
And if I may, another quick question about the TV variability, the 5 minutes and yes, so on. One of the problems I think that might be with your model somewhat is the interpretation of flares like 2155, where actually the entire luminosity, the apparent luminosity of the source significantly increased, was 10 times higher than what observed the years before. So I was thinking, I mean, in principle, could you expect to have to put a very fast variability with a very high luminosity?
Yeah, I
in a sort of turbulent or multi-cell.
Yeah. It wouldn't be from the turbulence. It would the very high flux would be from very high luminosity, would be from more energy coming down the jet, and then the turbulence would then allow fluctuations on top of that. So I mean, so the model has that in it. Answer to another question before was that I have a possibility to fluctuate the input energy according to a power spectrum.
Okay.
And so that would still, the power spectrum would still, be there. But to get the short-term variability, then you could still use the turbulence for that.
Okay.
I don't know if that answers your question very satisfactorily, but I'm not that pessimistic that it could be done. As I said, the main problem with reproducing the really short timescales of variability is that my cell sizes are all the same, and would have to have a range of cell sizes, or even better would be to actually simulate the turbulence, in a proper way.
Yes, yeah, but that's difficult. Okay, thank you very much, Alan.
All right, we're getting close to thanks for the question, and we're getting close to 10:30, so maybe room for one more question. Anybody? Jayshuang?
Yeah. Well, yes, I have a question. Oh, sorry.
Okay, go Jayshuang first, then Marco. Okay. Yeah.
Okay.
Yeah, I have a question. Maybe it's more broad. Do we know anything from M87 to the Blazars, to the connection? Because I was thinking M87 is well resolved. Is there any insight brought from these M87 observations?
Yeah, it's not an easy thing to do because we haven't yet really detected how the accretion disk emission connects with the jet in M87. We're hoping to do that in future EHD observations. So I really had hoped to get an observation of that, of how the jet comes off the black hole accretion disk ergosphere system, but that hasn't happened yet. So I would say that the main thing that I see that connects M87 to the Blazars is that in M87 you have a Lynn-Brighton structure to the VLBI. And here on the Markarian 501, you see a similar Lynn-Brighton structure. So I hope that that as we get better dynamic range with the Event Horizon Telescope, that we'll be able to see how this Lynn-Brighton structure gets created by plasma as it flows from the ergosphere region out to the places farther down the jet.
Okay, thank you.
Awesome, Marco. Yeah.
Yes, now just one very last comment on BLAC, very impressive optical polarization, which gets up to 45% or so. So the X-ray polarization is very low during these observations, but probably it was observed at other times, not as an upper limit, but as a detection. So the X-ray range then goes into the inverse Compton regime. This is the interpretation that we can give now of your slide. I don't know if you can show it again. It's very impressive. But my question is that now the polarization, which is getting to 45%, means that the optical emission, which is the synchrotron emission, given the fact that the X-rays are in the Compton, is really dominating the whole thing. So we have a single blob or a single cell which is dominating the emission. So I think it's very impressive. So can we?
Yeah, and very, very unexpected.
Right. Can we learn something more about this? I don't know whether there is.
Well, I think what we can do is take wild stabs at models, which is what was done in the paper. It was it had some kind of a magnetic spring that this is from Haocheng Zhang, his collaborators who were co-authors on the paper, that they have some kink instability that creates some kind of magnetic spring.
Right. But is this a sort of the first time that we detect something so dramatic?
Yeah. I've never seen anything quite like this.
Yeah. Very impressive. Yeah. Okay. Thank you. Yeah.
Cool. And maybe, all right, maybe I'll take a very last question. Just could you say anything about future prospects for EHT or VLBI, space VLBI? How much better will things get on what kind of time scale? What do you expect to happen next?
Well, there's a working towards an anticipated NASA call for proposals for next Explorer sort of missions next year. a group led by Michael Johnson is working up a proposal to get a space antenna with high sensitivity to go along with EHD, and then you can start to see smaller structures, and then you hope that you'll see some changes in those smaller structures when you see X-ray outbursts or gamma ray outbursts or something like that, to pinpoint where they're coming from, and also measure the polarization to see what the magnetic field is doing. There's a X-ray Paulo Safita is proposing in Europe an X-ray mission that would be a lot better than IXPE to measure X-ray polarization, but a wider range of energies with higher sensitivity. So there's some things in the works that, if they end up getting approved in these difficult times, and it would be very nice to see what they can tell us about blazars.
Right. Okay. All right. Thanks a lot. I think it's 10:30 and I have to disappear also, and other people probably do too. So we'll call it quits. And thanks for all the discussion for everybody who listened. And Alan, thanks again for an awesome talk.
Yeah, thank you.
It's pretty exciting. Okay. All right. And we'll see each other next time. Okay.